I've put the notes over here so you can follow it directly. I'm using the same notes here. Okay, so these are often called this SIG is for single input change. Okay, so we assume that only one input is changing at a time. So accordingly, we looked at this machine. So yeah, so this machine we had studied last time. So do you have any questions about the uh, behavior represented by this machine? Are you okay with it? Do you understand the behavior that is represented by this machine? Yes? Are you okay? All right. So note that over here, so these states which are put in bold, these are the stable states for the inputs in the column. These are the stable states. So we can think of these as the present state. Okay. So the stable states represent you can think of those as the present state, just as we so now this table looks very similar to the table for incompletely specified. Oh, I hope just let me check. I hope has someone started recording? Okay, yeah. Okay, so this is very similar to an incompletely specified FSM. Okay. So we've already studied the behavior of this. So for this, can you form the compatibility graph? So you can, so this is the compatibility graph for this machine. So you can see that, so best is, why don't you try to construct the compatibility graph for this machine. You know how to do that, so just do it in the same way. Okay, just do it in the same way, and you can then post it in the chat window. So just create the so this is called a flow table. So we are going to reduce the flow table, and we'll follow the same procedure. So why don't you create the compatibility graph, or what is also called the merger graph. So you can prepare the merger graph and you can post it here. Okay. So you can post the merger graph here. So are you done with it?
So can you show the screen once more?
Yeah, I can. This is the screen, but you can see it yourself. I've already posted it. So if you go to notices, it's already posted in WVCM. So you can see
Okay,
it from
okay.
there. So just first, of course, for this it is already shown. So maybe we can just see what is happening. So if you look at it, so one, so if you look at it, one is compatible with all the other states. So we have got five states here. So if you look at it, the row of one doesn't have a conflict with any other row. So as you can see over here, it is compatible with all the remaining states. Now let us say 2 and 3. So are 2 and 3 compatible? So as you can see, um, so if you see the input for 0, 0, so this is a don't care. Why is this a don't care? Can anyone tell me? Why is this a don't care? Why is this entry for state 3 a don't care? Can anyone tell me? Yeah? This was explained yesterday. Why is it a don't care? Yes, someone please try to answer. Why is this a don't care? Can someone tell me?
Because we can minimize it afterwards.
No. This don't care comes from the construction of the flow table. This don't all of these don't cares come during the construction of the flow table. So why do you get this don't cares? Can you tell me? Just it was discussed yesterday. Just try to recall. Just try to figure out and tell me. Why do you have this don't cares here? Anyone? This is important actually. It comes from the definition of this mode of operation. So can anyone tell me? Well, then let me just highlight the important part, that is SIC. What does SIC represent? Yeah. What does SIC represent? This you can tell. Hello? What does SIC represent? Can anyone tell? Aryan, can you tell?
Single input change.
Single input change. So look at this. This circle states are the stable state. So when you have single input change, see, you have got 2 bits here to represent. Actually, no, sorry. You have got 2 bits to 2 bits for the input encoding. The input is encoded in 2 bits, right? So single input change. So any one of these 2 bits. So what you can see is that. So you can if your if the input is encoded in k bits, okay, then first question, size of what will be the size of the input alphabet? Yeah, what will be the size of the input alphabet?
2 power k.
It is 2 to the power k, right? The next point, for a given symbol, for a given, so let us call this, so for a given x element of how many symbols of so how many? Can you answer this question? How many will be adjacent to gamma? To x? Yeah? How many will be adjacent?
K symbols.
K symbols. Because this is encoded in k bits, right? So each bit can change. So that is k. So you see over here, this is and the adjacencies. In each case, number of adjacent, these are 2, alright. So alright, so that is the situation. So I hope you understand why you have this. So if you have, so for this mode of operation where you have a single input change, only, these are the only, this circled places, these are the only, transitions that are possible, because all other transitions involve change of more than 1 bit of the input, right? So those are actually not reachable directly. You can reach them if you go through other states, but those are not directly reachable. All right. So that's why you leave those as don't cares. All right. You leave those as don't cares. So now what you see is that, so if we get back to if we get back to this, so now you can see that 2 and 3 are adjacent, because as you can see, you don't have any conflict between 2 and 3. So now, so 4 and 5 are also adjacent. Now let us consider 3 and 4. 3 and 4, should they be adjacent or not? Yeah. So can you tell me whether 3 and 4 should be adjacent, or should they not be adjacent? Yeah. What can you say about the adjacency, or sorry, I shouldn't say adjacency, rather I should talk about the compatibility. What about the compatibility of 3 and 4? Are they compatible? So
Dependent on 3, 5.
yeah, dependent. So now you look at the compatibility of 3, 5. So depends on 3, 5. Okay. So you can say depends on 3, 5. So now you look at the compatibility of 3 and 5. Are they compatible? Yeah. 3 and 5, are they compatible?
Yes, sir.
Oh no, they are not. 3 and 5 are not compatible. Look at this. That the output is 1, the output is 0. They are not compatible. Huh? You understand? 3 and 5 are not compatible. Do you understand that 3 and 5 are not compatible?
Yes, sir. Output is 1 and 0.
Not compatible. So this is also not compatible. So here you find that there is, 3 and 4, 3 and 5. So similarly, you can consider the compatibility of 4 and 2. So 4 and 2 also find that it is dependent on the compatibility of 3 and 5. So 4 and 2 are not compatible. So this is your, so now you know how to proceed. So why don't you, so you know how to proceed. So why don't you, complete the design? Why don't you complete the design for this? Just try to complete the design. Can you just do it? I mean, it is given here, but just try to do it on your own. So just try to do it on your own. So you have, so let us see. I mean, if you look at this, you can see that, this is one grouping that you can do. And this is the other grouping. All right. So these are two groupings, and in fact, that's exactly what is shown over here. So if you like to maintain the same, so it is 2, 3, yeah. And here you have 1, 2, 3. So these are the groupings. All right. So can you just form the reduced machine? You know how to form the reduced machine. So can you do that? Are you doing? Have you done it? Everything is explained here. But have you been able to do it on your own, although it is shown here? So let us just look at, so 1, 2, 3, so this one, these are, so for 1, this is the stable state, so this contributes to this, so you can sort of say that this contributes to this contributes to this, and this contributes to this, and this one, sorry, this one contributes to this, and this one contributes to this. So this you can see, right? Now, so the output here, this one is unspecified, right? So this one has been chosen to match the output of, the stable state. So in this case, as you can see, the outputs are, maybe I can just, these are chosen to match all right. Now why do you choose it to match this? Can anyone say why we should, why it is done that way, or why that is a reasonable choice? Can anyone suggest why that is a reasonable choice? Yeah. Is that a reasonable thing to do? Can anyone give an opinion? Yeah. Vaishnavi, would you like to give an opinion? Are you there?
Yes, sir.
Yeah. So, do you have, would you like to give an opinion? Is this a reasonable thing to do? Yeah. What do you think? Srijan, would you like to give an opinion? Srijan? Is that a reasonable thing to do? What do you think? Yeah? Any suggestion? I can't hear you in case you are speaking. Just say something, I mean. Would you like to say something, Varun?
Sir, I'm thinking.
Yeah, Varun, would you like to say something?
Sir, I'm thinking about it.
Yeah. Aryan, any suggestions from you? Aryan Singh?
Maybe it will make the circuit simpler.
No, there is a more, more basic and, fairly obvious reason. Just see if you can. It is a pretty obvious reason. It's a very simple and obvious reason. Just see if you can identify that. Anyone? See, in this case, it is, I mean, probably it's less of a problem. But I'll tell you, see, the output of beta, what is the stable output of beta, for example? What is the, so from this table, what do you see? What is the stable output for beta? That you can certainly tell. What is the stable output for beta?
0.
It is 0, right? Now suppose this is not 0. Alright, suppose it is not 0. then let us see what can happen. So here you have say alpha. What is the stable output for alpha? It is 0, right? Stable output for alpha is 0. Alright. Now suppose you had kept it at 1. Then you find that the stable output for alpha is 0. Stable output of beta is also 0. But in the intermediate situation, you have a 1 which is very short-lived, because as you can see this is an unstable state. Okay, this, as you can see, this is an unstable state. So it would be like this. So you have alpha 0, so this is a glitch. Okay, so you have, the output is 0, then it is 1, and again it becomes 0. So this is your, these glitches are undesirable. Okay, these glitches are undesirable. So it is better to choose the output of the intermediate state to be the same as the output of the stable state. So that is exactly what has been done to avoid such glitches. Alright. So that is another important point to note, evidently. Okay. So now so this is how you can reduce the transition tables, right? So does anything more remain to be done?
Encoding of the new states, alpha and beta.
Yeah, that's right. So state encoding. You need to do state encoding. Now in this case, actually the state encoding is relatively simple. Why? Because you have just two states, right? You can distinguish them with one bit, and the good thing is that these two states are going to be adjacent, okay, in either case. So here what you can say is that alpha using a single bit. Then, or rather I can say, both the encodings are or will be adjacent to each other. All right, so this is actually a very important point. Both the encodings will be adjacent to each other. Why is this important, or is this important? Is this important? Can anyone, once again I'll ask for an opinion. Can anyone give an opinion? Is this important? Yes? Can anyone give an opinion? What do you have to say? Is this important? Someone just try. Ritovan, would you like to give an opinion? Yeah? Anyone? Srijan has posted something. Yeah, so Srijan, can you elaborate? You have posted something, so why don't you speak up? Can you elaborate? Yes, Srijan, would you like to elaborate? All right, so what happens is that if they're not adjacent, because you do have transitions, so basic point is, let us consider a transition. Say, suppose from Si to Sj present in the okay, so you consider such a transition which is present in the state transition table. All right, now if the encodings are not adjacent, then the transition from Si to Sj will not be direct. Following the single transition rule, you can say, following the single transition rule. Why? Because your delays, see, you have this primary inputs and secondary inputs. Secondary inputs are state encodings from state variables, and you have secondary output, that is the new values of state variables. Alright, these are the new values of the state variables. So, you will not have a direct change, alright. So, in other words, you will have an intermediate state which might behave differently, alright. So there you have a problem. And as you can see, in the original table, each stable state has exactly k adjacent, k defined entries, unstable defined entries. But in the reduced table, you have more defined entries. Basically, you have, so what you can see is you have 2 to the power k minus 1 transitions. In the reduced table, whereas you have k in the original table. So you have a problem here. You have to handle this problem carefully. Otherwise, your machine will have will exhibit so improper state assignment will cause the machine to exhibit unexpected All right. So this is a very important point to note. So we'll look at this issue in the next class. Okay, we'll look at this in the next class. Okay, I think we can stop now.